Hello everyone, I'm Dr. Tanu Gupta, Assistant Professor, Department of Mathematics, and I will just be giving a lecture on Introduction to Graphs. And it is a very interesting field, a very fascinating field. And so basically, what are graphs is basically you study. It's a study of networks and connections which are represented by vertices and edges. So basically, the vertex sets, which we represent by nodes or small circles, they should not be empty, right? And then joining those vertices, we have certain edges. You can see them as interconnecting lines, though they need not be lines. So they can be of, just a way of connecting two vertices. It's a very interesting field which has applications over fields of computer science, social science, biology, and many more. So how does this field came into existence? Now that is also a very interesting case where this field was accidentally discovered as a solution to a problem which was given by Euler. And there was a very famous problem which was the Königsberg Bridge problem. And Euler solved that problem in negative. And he said that the problem has no solution, uh, and the solution he gave, he used graphs in that, and he used a structure of nodes and interconnecting lines which later transformed into vertices and edges, and it paved the way for a new field of graph theory. So let's discover that and let's move on to it. So starting with, we first discuss is what is actually was the Königsberg Bridge problem, which led to the discovery of the whole exciting field of graph theory. So Königsberg was a town or a city in Prussia, which is now Russia, and it was set on both sides of Bregel River. And so it has two main islands, and they were connected to each other by 7 bridges. So what did the Bregel River did was it divided those land masses into further into 4 land masses, and they were and the problem was you need to find a way, was is there a way possible that you could walk through the entire city, means you can cross all the land masses by crossing each bridge exactly once and only once. So because the Bregel was dividing into 4 landmass, you can start from any landmass, you can take bridge, one bridge at a time, and you can just end up by crossing all the bridges onto some other landmass. So this was the problem, and Euler stated that this problem has no solution, and the way he presented the solution was very exciting, and that's how graphs came into existence. So this is how the map is, and you can see that 1, 2, 3, 4. So these are the land masses. The Bregel is dividing the city into, and you can see these bridges: 1, 2, 3, 4, 5, 6, 7. There are 7 bridges, and this is how the problem was. That you have to start with any landmass, and then you take this bridge, then you go over to this landmass, you take another bridge, then you take another bridge, and that's how you have to cover. And so you have to take only every bridge exactly once, and you have to get off at the other landmass. So Euler realized that if you're trying to find a path by drawing the layout of the bridges and connecting them various ways, it will take a lot of time. And actually, it is not needed, to find out the layouts of the bridges, find out different way possible. So he actually made that problem into a graph problem. So he took every bridge as an edge, and all those land masses, they become a node or a vertex, and those land masses were represented by letter A. And so in the context of the graph that the problem reduced into had 4 vertices and 7 edges for the bridges. So the graph of that, it somewhat looked like this. You can see this is A, B, C, D. These are the 4 land masses that Prejal was dividing the whole city into. And you can see the bridges. 1, 2, 3, 4, 5, 6, 7. So this is how the bridges is. Also, I told you that it is not necessary that you have to draw the edges with a straight line. We have a curve over here, just a medium of connecting the 2 vertices. So this is how the interesting. Now, if you see, the very interesting thing over here is that every vertex that we have over here, it is connected to odd number of bridges, right? So it is 5 bridges over here, 3 bridges over here, 3 bridges over here, 3 over here. So every vertex is connected to an odd number of bridges. Now Euler realized that if you want to, visit a landmass, okay, and then you come through a bridge and you don't want to go back using the same bridge, okay, then you have to take some other bridge. That means if you so for that, the number of bridges on each landmass, that should be even in number, but that was not the case here. Every vertex had odd number of bridges. So Euler said that it is not possible that you start with a vertex, take every bridge exactly once, and you get off some other vertex, because every vertex over there is here is odd in nature. Okay, it has odd number of bridges on it, and that's how a whole, he said that solution to such a problem is not possible. And so however you try, however routes you try, it will be never possible, because the vertices are odd in nature. Now we'll discuss with what you mean by odd and even vertices a little later in this lecture. But just to the crux of it, that a very layman would understand, if you want to come to you visit a landmass using a bridge, right, and you don't want to take the same bridge back, you have to find some other bridge out, right? So that how was the Königsberg Bridge problem was. So what did Euler used was, he used letters to represent the larger situation of land masses, used lines to represent bridges, and concluded that no such solution was even theoretically possible. And in the meanwhile, he sparked a new branch of mathematics called graph theory, where graph is simply a collection of vertices and edges. So now moving more forward to formally define the graph for us. A graph is a set of points called vertices together with a collection of lines called edges connecting some of the points. So main thing is that the set of vertices should not be empty, okay, and graphs, then the set of vertices could not be empty, the set of edges could be empty, and it is also not necessary that all the vertices are connected with each edge. So maybe there are certain vertices which are not connected with an edge. So we generally write graph as the vertex set as v of g, edge set as e of g, and the number of vertices, it gives the order of the graph, and the number of edges, it gives the size of the graph. Now for us, the graph means that we are not allowing multiple edges or loops. Loop is something, an edge which is starting and ending at the same point. So we're not allowing that. Okay, for our graph. For that, we are defining a pseudograph. So a pseudograph is basically a graph, but here multiple edges and loops are allowed, right? So for us, a graph is a structure which is having vertices and edges, but no loops or multiple edges. Multiple edges means more than one set of edge between the same vertices. So if two vertices are joined by an edge, then they are called adjacent. Okay, and two edges are adjacent if they have a vertex in common, right? So the degree of a vertex right, is the number of edges incident on that vertex. So basically number of edges which are lying on that vertex, connected to that vertex, that gives the degree of the vertex. And since in a loop, the starting and the ending vertex is the same, so what we do is for every loop we count 2 in a degree of that vertex. So we add 2 to the degree of the vertex if there's a loop on that vertex. If the degree of a vertex is odd, then it is called an odd vertex. If the degree of the vertex is even, then it is called an even vertex. In case the degree is 0, though 0 is an even number, we called it an isolated vertex because of the obvious reason, because isolated means it is not connected to anything, and that's what the case it is here. The degree will be 0 if there is no edge from the other vertex to that vertex, so it will be an isolated vertex. Now the degree sequence of the graph is nothing but you find the degree of every vertex and then you write all those degrees in a descending order and in form of a list or a sequence that forms the degree sequence of a graph. So let's see these definitions in form of this example over here. So if you can see, this is a graph where we have 5 vertices A, B, C, D, E. So the vertex set of the graph has 5 vertices A, B, C, D, E, and this graph has 4 edges. You can see the edges AB, AD, BD, BC. So this is the edge set of the graph. So this graph has 4 vertices, 5 vertices and 4 edges. Now let's find the degree of each vertex. So degree of each vertex is like vertex A has 2 edges on it, right? AB and AD. So its degree is 2. Similarly, vertex B has 3 edges on it, AB, BD and BC. So the degree of this vertex is 3. Vertex C has just 1 edge on it, so its degree is 1. Vertex D has 2 edges again, AD and BD, its degree is 2. And vertex E has no edge on it, so it's an isolated vertex with degree 0. So since A has 2 degree, it's an even vertex. B has 3 degree, it is an odd vertex. C has 1 degree, it is an odd vertex. D has degree 2, so it has even vertex. And E, as I told you earlier, is an isolated vertex. So the degree sequence of this graph would be 3, which is the highest degree, of comma 2, comma 2, comma 1, comma 0. So this is the degree sequence of this graph. Also, you can see this vertex A and D are adjacent to each other because they are connected by an edge AD. Similarly, vertex A and B are adjacent because they are connected by an edge AB. So this is the edge which is joining the two. Vertex A and C are not connected. They are not adjacent because there is no edge between the vertex A and vertex C. Similarly, edge AB and AD are adjacent because they have vertex A in common, right? So this is the concept of adjacent of vertices and adjacency of edges. Moving on, we define another thing which is a complete graph. So what is a complete graph? A complete graph is a graph in which every vertex is connected to every other vertex. So that means between every pair of vertices of the graph there is an edge, right? So this is a complete graph definition. And we denote a complete graph of n vertices by kn. And so every vertex in Kn will have degree n minus 1 because it will be connected to the other n minus 1 vertices. So every vertex will be connected to other n minus 1 vertices, and mind you, we are not repeating any edges in our graph for our definition of graphs. So every vertex in a complete graph will have degree n minus 1, and the number of edges in a complete graph are n into n minus 1 by 2, because every vertex is connected to any other vertex. So when you are counting the total number of edges, so it will be n into n minus 1, but every edge will be counted twice, so you divide by 2. So you can see some of the diagrams of the vertices of a complete graph. So K2 we have drawn as a straight line, K3 is a triangle, K4 is a square with diagonals connected. Then we have K5, K6, K7. So these are some diagrams for your graphs of complete graphs with vertices 2 to 7. So moving on. Let's see, the next is we just had a look at the complete graph. Now we have something called the bipartite graph. So bipartite graphs is basically the graphs which divide, the vertex set into two disjoint classes where, the edges are in between in between the classes, not among the vertices of the same class, but in between the vertices of the two different disjoint sets that we created. So basically, a graph is bipartite if you can color the vertices red and blue in such a way that each edge connects a red vertex to a blue vertex. So here what we have done is we have made a set of red vertices, a set of blue vertices. So there are no edges among the red vertices or among the blue vertices, but the edges are only possible between a red vertex and a blue vertex. And if as by the definition of complete, if every red vertex is connected to every blue vertex, then the graph is called a complete bipartite graph, and it is denoted by KMN, where M is the set of, say, red vertices, M is the number of red vertices, N is the number of blue vertices. So then KMN is a complete set of it's a complete bipartite graph. And KMN obviously will have M into N edges. So this is, I have just let this is some examples of bipartite graphs we have drawn. If you can see that in all these graphs, every edge has different color vertex as the endpoint, right? So every graph is a bipartite graph, and the bipartition sets consist of the set of red and vertices one set of blue vertices from the other bipartition sets. So you can see every edge, all the edges in the graph, they have different color vertices as the endpoints. Therefore, the graph is a bipartite graph. They are not complete bipartite, right? Not all graphs are here, not all graphs are complete bipartite. For example, here this vertex red is not connected to this vertex blue. So though it's a bipartite graph, but it is not a complete bipartite graph, right? But this is an example of a complete bipartite graph because every red vertex is connected to every blue vertex. So this is how the bipartite case goes. So this is, we have drawn some diagrams for you. This is K23 where in bipartition sets we have two vertices in one set, three vertices in the other set, and there is a line segment joining every vertex of two vertices to every vertex in the set of three vertices. Same we have K33, K35, K26. These are the all examples of complete bipartite graphs. So towards the end, we come to a very interesting lemma, which actually has a various corollaries. It is used in various results. So this is the Euler's handshaking lemma. So Euler's handshaking lemma says the sum of the degrees of the vertices of a graph is equal to twice the number of edges. So basically it says if you find the degree of all the vertices of the graph, take their sum, then that sum will be equal to twice the number of edges the graph has. Now that is obviously because when you are finding the degree of a vertex, right? So you are counting the number of edges that are incident on that vertex, right? But every edge is incident on two vertices. So suppose edge v1 v2 is also incident on the vertex v1, it is also incident on the vertex v2. So it will be counted once when you're finding the degree of vertex v1. It will be counted in degree of v1 also, and also in degree of v2. So every out edge is counted twice. So when you're finding the sum of the degree of all the vertices, also by convention for every loop you are counting twice already. So you're counting 2 for a loop in a degree. So when you take the degree of all the vertices and take their sum, you get nothing but twice the number of edges, right? And a consequence of this lemma is that graph of odd vertices are even in number in a graph, and which is very simple to prove again, because we know that sum of degree of all the vertices twice the number of edges, so it will be an even number because it's 2 times number of edges. Now if it is an even number, then the in that calculating the degree of vertices, we will also have odd vertices and even vertices. Now sum of the degrees of even vertices even number, right? Now sum of even number plus sum of odd degree of odd vertices, now then that total has to be even. Therefore the sum of odd vertices should be even in number. Now sum of odd vertices will only be even if the number of odd vertices are even, otherwise it will be an odd number. Therefore, to satisfy the Euler's hand-checking lemma, the number of odd vertices there should be even in number. So using this, we'll just answer this question also. So the question is, does there exist a graph with degree sequence 4, 3, 3, 1? Now if you just look at the graph, it has a degree sequence 4, 3, 3, 1. Now here we have 3 odd vertices, or even if you take the sum of all the degrees of the vertices, it will be 7 plus 3, 10 plus 1, 11. The sum of the degree of the vertices is 11, but that cannot be an odd number, right? We just proved the hand-checking lemma that this number should be equal to twice the number of edges, and number of edges cannot be fraction. So that means this graph is not possible. So graph with degree sequence 4, 3, 3, 1 is not possible, because we will have 3 odd vertices here, and in a graph we can only have even number of odd vertices. We just proved using a corollary of the Euler's hand-shaking lemma, right? Now the next question is, does there exist a graph with degree sequence 4, 3, 2, 1? Now here everything seems falls into place, right? Because when you take the sum comes out to be 10. The sum of the degree of all the vertices, it comes out to be 10. Also the number of odd vertices are 2, odd vertex of degree 1 and odd vertex of degree 3. So there's no problem as per the Euler's hand-shaking lemma. But you have to realize that here we are talking about graphs and not pseudographs. So a pseudograph would be possible. Like in earlier case, even a pseudograph would not be possible. Here, a pseudograph would have been possible, but the problem would be that we know that in a graph, now this is a degree sequence of a graph having 4 vertices, right? And we know that if a graph has 4 vertices, the maximum possible degree that a vertex can have is 3. It cannot be 4. So here we are wanting that vertex should have degree 4, which is not possible, because if it's a graph of 4 vertices, the maximum possible vertex degree of a vertex can be 3 and not 4. Therefore, even such a graph is not possible. So now you see that how important is not only to understand the Euler's hand-shaking lemma, but we also have to understand the concept of graph that we have taken. We have taken graph as a structure having vertices and edges, but we are not allowing multiple edges, we are not allowing loops. Therefore, such a degree sequence is not possible, right? So in today's lecture, give you a quick recap of what we did. So we learned that how Euler um, paved the way for graph theory. He's called the father of the modern day graph theory. What was the Konigsberg bridge problem? We learned about what you define by a graph, vertices, edges, what do you mean by adjacent vertices, degree of a vertex, degree or sequence of a graph. Then we learned about complete graph, bipartite graphs, complete bipartite graphs, and in the end we also saw what is an Euler's handshaking lemma. This is just the beginning, and a wide field is open to explore more. Much so more in the other lectures. So I am winding up this lecture today. Thank you everyone for watching.